Welcome back, Algebra 2. Let's talk about something that you may or may not have seen in science class before. I think it's a kind of a cool topic to talk about, which is half-life. And half-life is the amount of radioactive substance decreases over time. So what a half-life essentially is when you have a substance and it's the amount of time it takes for half of the material to decay. So let's say you have 100 pounds of, I don't know, any material really, let's just say iron. So 100 pounds of iron. And so how long would it take for you to have only 50 pounds left once it's decaying? So like deterioration and whatnot like that. So if you have 50 pounds left, how long did that take? Let's say, just throwing numbers out there, let's say it took 13 years. So therefore the half-life of iron would be 13 years. That's how that works. So make sure you write all this down. The half-life of a substance, the amount of time it takes for half of the material to decay. Alright? And half-life can range from, well, it's supposed to say range right here, no ranger. So it can range from a few seconds to millions of years, depending on the substance. So if you think about, let's just take a simple example. When you throw away trash, so certain things are biodegradable, like a banana peel or like an apple core. Those will deteriorate. Let's just throw out numbers. So let's take it takes them 20 some years, so 25 years to deteriorate. So apples and bananas and such like that have a shorter half-life than, say, something like a piece of plastic. Plastic is much more durable, it's going to stay in the environment, and that's why people don't want you to throw plastic away. They say, hey, let's take it, let's make something else out of it, because otherwise it's just going to sit in a landfill and take up space. Whereas apple cores and banana peels will break down and actually, you know, they're actually sometimes good for the earth, okay? It doesn't mean go litter everywhere, but you can throw apple cores and banana peels away, but you can't really throw plastic away. They like you to recycle it because of its half-life. Okay, it can withstand a lot here. Okay, what does this have to do with exponential decay? Well, a lot, because we're talking about material decaying here. Okay, example 2 says C14 has a half-life of 5,730 years. So A, it says determine an equation for the percent of C14 remaining in the original sample after X half-life periods. Okay, so we're going to use our original f of x equals a times b to the x power. So we have to be careful how we're using this here. So f of x is obviously the amount we're going to have left here, or excuse me, the time we're going to have here. And the initial amount, we don't know. We just know it's half-life. We don't know how much we started with, so let's just talk percentages. We're going to start out with 100% of the original C14, however much we have there. Alright, so we're just going to say 100 for a nice round, easy number. And we can always say that it's 100% as well, which is nice. Okay, B, our growth rate here. Well, excuse me, not growth rate, decay rate here. Well, since it's a half-life, we're going to end up with half of it left, which means either you can put 1/2 here as a fraction, or 50%, which would be 0.50, or just 0.5. Alright, so that's our half-life. Every time you use half-life, you're going to use your rate as 50%. Okay? And then x is going to be up here as our time, where x is the number of 5,730 year intervals. So x is going to be the number of 5,730 year intervals. Okay, so since its half-life is 5,730, we're not going to count it as 1, 2, 3, 4. 1's going to represent this many, 2 is going to represent twice that many, 3 is going to represent 3 times that many. So we're counting by every 5,000 years, if you want to think of it that way, which is a lot, but typically things don't deteriorate in 2 seconds. They have longer half-lives here. Okay, so we're going to graph this equation. So my suggestion would be to grab your calculators, and let's go ahead and plug this into our y equals screen. So let's clear out all our business here. If you have stuff in here, clear it out. And so we're going to put in f of x is just y, remember? So 100 times 0.5, oh my goodness, sorry, 0 Let's try that one more time. 0.5, okay, to the x power. Okay, and we're just going to remember in our heads that x is every 5,730 years. Okay, we can't really program our calculator to do that. So we go to our graph, and oh look, we have a picture. If you're in a funky window, go back to zoom and hit zoom standard, please, so that you get this same picture that everybody else has. Okay, now, so we have a picture there. Could we get a better picture? Yeah, I'd say so. We could probably zoom out. Let's zoom fit and see what happens there. So fit is 0. And I don't like that any better because it drops real quick and then it flattens out into a flat line. So go back to zoom standard. So C6. Okay. And then we're actually trying to graph it on our coordinate plane over here. So let's actually move this, and we're going to, let's move it all the way over here. Then look at our table of values. So let's write down a bunch of xy's, as many as we can fit on here. So xy, okay. So 0, 100, depending on how we scale our graph, because we do have choices here. They're completely naked here, so we can do whatever we want with them. So I'm going to go ahead and do, down here at the bottom, let's see, if we do 1, 2, 3, 4, that'll only give us 4 years. So let's, down here, I'm just going to go by 1. So every hash mark is going to be worth 1. So 1, 2, 3, 4, 5, 6, 7, 8. And don't forget, I would like these labeled. I'm kind of squeezing in, not too much room down here. But that's going to be the number of 5,730 year intervals. Hopefully you left yourself a little bit more room, but I would like all of these labeled. So number of 5,730 year intervals, and then our scale up here along this y-axis. Well, let's be smart about this. Let's make a pretty graph. We're going to really start here at 0 because you can't really go back in time. So let me see what 0 is. 0 is 100. So we at least have to get this guy up to 100. So let's see if we just count by 10s. Let's see what happens. So 1, 2. Well, let's do this the proper way, I suppose. Let's count by, we want to get to 100. Let's count how many there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So let's go ahead and do 100 divided by how many there are, which is 13. And we get 7.69. Yuck, I hate it. Even 8 I don't really like. So let's just do the next roundest number, which is going to be 10 for us. So let's go back to our table here. So we'll count by 10. So if you want to label these by 10, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, and 130. Okay, I thought we were going to get more than 13 in there, so, but that's okay. So these are, well, what does that stand for? That's going to be the amount of C14 left. So amount, I'm going to try and write sideways here. Amount of C14 left. Okay. Okay, so, and of course that's in percentages, so let me add that in here. So that is the percent of it left. Okay. Okie dokie, so let's start plotting points here. We have 0, 100 we're going to use. We're going to use 1 and then 50. And then we're going to use 2, 25. Ah, keeps turning off on me. There we go. And then we're going to use 3, 12.5. Notice these are all just getting halved. 4, 6.25. 5, 3.125. 6, 1.56, and then I ran out of room, but let's scooch this guy over, and we'll do at least, because our scale over here goes up to 8, we'll go 7, and then 8, and we'll just scroll down for these. So 7 is 0.78, and 8 is 0.39. Okay, so we can get rid of this guy, because we just needed it for the table. Okay, so now let's go ahead and graph. So 0, 100. 0, 100 is right here. And sorry, that's going to do that every time I try to make a dot. It thinks I want, I don't know, to hold it down. I don't know. So sorry if it does that again. Okay, so 0, 1, or excuse me, 1 to 50. So 1 gives you 50, which is exactly half of what we started with, hence half-life. Okay, 2, 25. So 2 and then 25 would be right about here. And 3, 12.5. That's what that says. So 3 and then 12.5, which would be right about here. And 4, 6.25. So 6.25 is right about there. Whoops. Sorry, it also likes to get rid of them. Okay. And 5, 3.125. So we're getting closer to the x-axis. And 6, 1.56. Getting real close. Okay, 7, 0.78. Even closer. But we're not on. Keep in mind that we're not on the x-axis here. And then finally 8, 0.39, as close as we can get without touching. So let's go ahead and try and connect these. Hopefully yours is a little smoother than mine. But remember, these will never touch the x-axis. As much as it looks like it's going to, I explained in the growth one that it's not going to touch the x-axis. It should look like our picture that we had originally, if you remember back here. Now, of course, mine's not going to be as pretty, but yeah, it dips down and then it hovers real close to that x-axis, so we're good. Now, like I said, we're never going to touch. I don't care how far you go out here. If you go out to 100 on your x-axis, it will never, ever cross the x-axis. It's going to get really, really close, but it's never going to get there. And this is a good example because if I do halfway to something, so I like to use the analogy, and if you ask me to do it tomorrow in class, I probably will, because it's a really good one. Let's say, you know, this is the race that I'm running, and here's my start, and here's my finish. Well, if I only allow myself to walk halfway each time, so I start at the start, of course, and if I allow myself to walk halfway to the finish, then I'm only right here, okay, clearly far from the end. And then I say, okay, from here to the finish line, I walk halfway again, but now I'm only right here. And then if I walk here to the finish line, if I only allow myself to go halfway again, I'm only going to be right here. And then if I allow myself to go halfway from here to here, then I'm only going to be right here. And then if I go halfway again, then I'm only going to be right here. And I could continue this pattern, and in theory, yes, I'm going to smack right into my finish line, but what is actually happening is I'm only taking half. And if I take half of something, there's still going to be half left. So will I ever get to nothing? No, because you can't take half of something and have 0. You always have to have the other half, which it can't be 0, or else that means you started out with nothing. Okay? It's a good analogy to kind of think about walking halfway to somewhere, which is exactly what half-life is. We're taking half of it away. And it's just asking you, how long is it going to take for half of that stuff to be gone, which for C14 in particular would be 5,730 years. Okay? Now, the only other thing that I want you to take from this is the kind of stuff that a lot of people use. People like biologists, people, any kind of science really, and any kind of people who work in, where they, what's it called, where they dig up fossils? Archaeology, my goodness. So that they can tell, okay, this is from this time period. That's how they figure all that stuff out. Everything has a half-life. So if they can figure out what their mystery substance is, they can figure out what its half-life is, then that limits it to, hey, it's this kind of substance, or it was from this time period. If they know the substance, they can figure out, oh, okay, well, there's half of it left, so it was 5,000 years ago when this thing was created. So a lot of different uses for this, so a lot of stuff is backed by mathematics, so this is why you need to know this kind of stuff. Okay, so we just have a few more topics to talk about, so I'm going to save them for another video, so hopefully you'll join me for the next one. Thank you!